So today we'll start a new topic. We'll start talking about conservation of linear momentum. Basically the Bernoulli equation, but in a different framework, and it will build on the stuff that you've already looked at in the last little while. That is, you've been looking at, for instance, conservation of mass in different coordinate systems, moving and deforming, etc. And so we'll draw on some of that, but to be able to conserve something different from mass, we'll look at conservation of momentum. And of course, we know that from what we talked about in terms of fluid statics, the equations we had, dp dz is equal to minus unit weight of fluid, that is derived basically from F equals ma. And so Bernoulli is also related to that, and also conservation of momentum, which is really what Bernoulli is doing, therefore is related to that as well. And so all we'll do is we'll extend it into a slightly different reference frame, a generalized reference frame, not just a stream tube, but more general. And I don't know why that's not running. Oh, it is now. Okay. And so in the same way that we could use Bernoulli to look at the jet lev, we can also use it not just to define a streamline that we solve along, but we could define a control volume, which we look at the fluxes not of mass now, but of momentum instead, that go across that. So that's kind of our goal maybe for today. Well, we looked at some videos. Let's take a tack today that we maybe recap what's gone from last week, and to some extent the week before, but mainly last week in terms of Reynolds transport theorem, and then talk about how we're going to take that the next step and why we might want to do that. So we can come back and chat about our motivation for doing this. So Reynolds transport theorem is just a generic way to be able to say something about fluxes of something into a closed container. That closed container could be a bucket, it could be the jet lev, it could be a differential cube, dx, dy, dz, and we can choose a variety of properties that we might want to conserve. And in the case where we did it for mass, then our conserved quantity was equal to mass. And so when we substituted that into here, then lowercase b was equal to 1. That means that each of these components here ended up being equal to 1. This is the large-scale system, which for us is always equal to 0. And so the generic way of looking at this expression is a concatenation of this into this. And we know that the individual components of this are that these represents a rate of change of something. And we can probably write it better than that. It's really an accumulation of mass. And this second term represents mass in minus mass out. And when you add these components to each other, then the net change, net evolution of these has to be equal to 0. And so all we need to realize is that this dot product here, which we'll deal with here, means something relatively specific. Perhaps it's worthwhile drawing a geometry. And so this dot product represents, the normal to the boundary. And so if the flow across that boundary, the mass flow across that boundary, which is density times area times velocity, so density times area times velocity. If it's congruent with this, if they're both aligned with each other, then the dot product of two components aligned to each other is just equal to this magnitude. And this, of course, is the mass flow rate, what we'll call m dot. And so if it's coming out of the volume, then it is what we'd refer to as being positive. If it's going in the opposite direction, where this is the unit normal on that boundary, and it's flowing in this direction, rho VA, and I guess this would be 1 and this would be 2 maybe, just because they're different sides, then because the normal and the direction of velocity are in the opposite directions, I guess, yes, this is the normal and this is the direction of velocity, then it's equal to a negative magnitude. And so we just have to be wary of the sign convention that's used, that if the mass flow rate, and this is also a mass flow rate here, so this would be the mass flow rate into side 1, and this would be mass flow rate out. If it's out of the system, it's positive, and if it's into the system, it's negative. So that's what this term here represents. And in shorthand, we can write it as this, and in even shorter hand, we can write it basically as this, where this is just the sum of the mass flow rates. So that's all this is. The rate of change, or the accumulation within the system, is given by this derivative. And so the only important thing to realize with that is that we can, if we want, split that, and this can become, in our shorthand, the rate of change of density with a given volume plus the rate of change of volume with a given density. That is density, not P. And so this would be, an analog for this would be a balloon. The volume's changing of the balloon as it expands, and so it's getting larger. And the analog for this would be putting air into a compressor or a diver's tank, say, that isn't deforming, but where the density has to increase as you put more mass into the system. And so these are the two components that can change. And if we look at the sign convention for those, these are, by definition, this is change in density with time. The overscripted dot is just that. And so the only thing to realize that positive values of density change and volume are given with an increase in volume or an increase in density. And so that's the sign convention. So when we apply this, and so this overall expression, I guess we would use it something like this. It would be rho V plus V dot rho plus sum of mass flow rates equals 0. So this is the expression that we'd use and you have used. Then we just have to be mindful of the fact that this sign convention gets applied to this, and that this sign convention gets applied to both of these components. Positive is an increase in density, increase in volume with time, and this is positive if it's flowing out, and negative if it's flowing in. And if you do that accounting, then everything ultimately works out. So that's the deal for this. I guess the one thing that we haven't mentioned here is that it matters what the frame of reference is that you choose. And in that regard, we've had this kind of hokey diagram that I've drawn of a boat moving along. I guess the boat floats on something. And in terms of, we used the example of this fireboat that is shooting out water at some velocity, and that is moving physically along at some velocity of the control surface. So in other words, this boat is moving at some velocity VCS. It's a vectoral component. Here it's only one component. It's in the x direction or y direction. But to a static observer, if you look at what this looks like, then if you look at what's happening to a particle of water as it's shooting out of this cannon, then this is the static observer's view of what's going on. So it's just the sum of how fast the boat's going and how fast the thing is being thrown out of it. It's just like going along on a trolley. Trolley's going at some velocity. You throw a ball at some other velocity. Those are these two velocities. And together to a static observer, which the trolley's going past and the thrown ball is going past, it looks as it's really going at this particular rate. And this is the across-boundary velocity that we have to use in the equations that define mass in equals mass out. So that's the other wrinkle in this. So that's why we are interested in understanding something about substantial derivatives, this uppercase dv dt, or dt dt, as we did in the example with the borehole sonde going down in the borehole. Okay? So that's the recap in terms of what we're doing, or what we have done in the past. And so what we might like to do now, and just for a break, let's go back to some of the things that we looked at. A Pelton wheel. One of the reasons that we're interested in conservation of momentum. So conservation of momentum is the same as a jet engine pushing the truck off the apron at San Francisco International. You get hit in the chest by moving air. It stagnates. As it stagnates, it loses its velocity. By definition, dmv, momentum, change of momentum with time is, or space is what changes the force that's acting on the system. And that's exactly what's happening here. You have a jet of air which goes into these cups. The air would be stopped by the cups if the cups didn't move, but if it's on a spindle, then it can move. And it turns out that these cups will actually, in a frictionless system, will be going at exactly the same speed as the air will be traveling. So I want to pause that. No, I don't. Yeah, I do. Okay. Jet lev we looked at before, and so you understand exactly that. It's analogous to the jet engine pushing the truck off the apron. In this case, it happens to be a higher density fluid, which if it's going at the same rate, its momentum will be higher because it has higher mass if the volumetric flow rates would be the same. And you can use it just to react against the surface, which in this case is the water, which is quite rigid. And it's like concrete, apparently. Well, if you've jumped off a high diving board, you can appreciate that. And so it's reacting against the surface. And if you look at this Mythbusters, which is, as I just noticed yesterday, that this is one of the questions on last year's second midterm, was to look at basically the idea. It's like a rocket, right? If you go into a lab, they should always be attached vertically, strapped to a table leg or something. Because if they do go off, sometimes referred to as the sleeping giant in these safety flyers that you have posted in some labs, and that is that if it does fire, then it can travel. And the question is, how violently can it travel? So this is just a little demonstration. They've got a guillotine that shears decapitates the top of the cylinder, and it does something. And so as we go through this, you'll see. I guess I could turn the volume on.
The valve has sheared clean off, and that's a very good sign. It looks like the cylinder flew straight and true, but did it have enough thrust to crack the wall?
Oh, God.
Now there's a bit of humor for the morning.
It was the lard that did it.
At 40 miles per hour, the air tank turned the cinder block to cinders. It even put a fair dent in the wall 6 feet behind it.
It totally. I mean, it didn't go all the way through, but it went through this one and it was gone. It's working its way through that one.
I was ready to see this as not possible. I was totally expecting it not to actually work, because it's one of those apocryphal tales, and everyone we talked to had heard the story, but no one knew anybody that it happened to.
That's right. Is it urban myth or not? Apparently not, right? Because it doesn't. So we're going to turn our attention to maybe try and be able to figure out exactly how we would evaluate that. Certainly you could use Bernoulli, and I'm pretty sure that maybe one of the prior questions that we've done in class, recorded in class, was a a tank of a certain pressure, looking at the velocity that would come out of the nozzle. It's a closed system, so by definition, it's not in steady state. It can't be in steady state because there's not a new supply of fluid going into it that gets pushed out at the end. It's a closed system, and so it's not in steady state. It's depleting the reserve of pressurized gas as it goes on. And so we have to think about how exactly we would do that. But we can basically use conservation in the same way that we have used it for Reynolds transport theorem to be able to look at that. And so what we'd like to do is that the component that we'd like to conserve is equal to this extensive quantity, which now is going to be mass times velocity. Velocity, of course, is a vector. If we go up here and I do this, let me clean up this since I can, right? So there's no reason why I can't get rid of some of this. And so now, if we realize that this conserved quantity is equal to this, then this is equal to mass times velocity divided by mass. And so this is going to be mv. This quantity here is going to be just velocity. And this quantity here is also going to be velocity. It becomes a bit more difficult because before the quantities that were here were just 1. And so 1 is clearly just a scalar rather than the vectoral quantity. So velocities have 3 components, x, y, and z, in our right-handed coordinate system. And so if we use that, we can note, first of all, that in terms of Newton's second law, we can also rewrite this as mass times, actually let me do it slightly differently. So by definition, this term here is equal to the sum of the forces, because this term here is exactly the same as this term here. And that what we can then do is we can now look at these other individual components that we'd like to look at here. And so if we write this down here where I have a bit of space, just writing it out in longhand, sum of the forces are equal to, so this is just this. Forces is a vectoral quantity. A rate of change with time of an integral, which is density times velocity time integrated over the volume. So V through score is this, plus this term here. And this is the only term that we'll worry about. It's going to be an integral over the control surface as opposed to the control volume. And it's going to be the product of density, a velocity, a dot product of velocity, integrated over an area. And so it starts looking a little complicated, but all we've done is we've substituted this in here. So let's maybe look at these individual components. So first of all, we're going to think about the geometry that we have. I guess that'd be a useful thing to draw. So the geometry we have is just a control volume. Could be any shape we want. Let's make it a rectangle just because it's a bit easier. The control volume is the interior of this. The control surface is the exterior, the boundary. So that's what these two components are. We're always going to look only at steady state. So we're going to set this to being equal to 0, just because we don't want to deal with a more complicated case. And so if that's the case, then we only have this component left here. And so what we can do is we can think about what these individual terms are. We said before that if we look at the product of density and the area and the dot product of velocity, then these three things together, by definition, are a mass flow rate. And so if we go up here, I guess I erased it. But certainly an area times a velocity is, in units, this is L squared. This is length over time. And this is mass per length cubed. And so length cubed is just equal to mass per unit time. So this definitely is a mass flow rate. And so if we identify the components that are associated with this, this is one of them, this is another one of them, and this is the other one. And so what we could do is we could write this expression out basically as sum of forces. I should underscore this, right, because there are three components, x, y, and z. And this is going to be equal to an integral over the control surface of velocity times mass flow rate. And actually, we've already taken care of the mass flow rate requires that we do this integration, I guess. And so this term here, we probably don't need to have there. You get rid of it. And so if that's the case, what we basically have is something that represents another summation. This is a vector. This is a scalar quantity coming across the boundary. And we can worry about the sign convention that we might want to have to apply. So I suppose, just like before, we could end up having a flow at some velocity v1 that goes across here, and a flow at some velocity v2 that goes out here. We have the normals to these boundaries, which we already said something about in terms of these unit normals, which are just a vector that's unity in length. And I suppose in this particular case, we also need to define something that is a coordinate system. And so it would really be a cube, I guess, if we're looking in 3D, but we would have forces in the x direction are equal to the velocity in the x direction times the mass flow rates across that surface. Forces in the y direction and forces in the z direction. So we're just summing individually those individual components. And so these are the three components that will go into this expression here, and the three components that are in this as well. If we wanted to, I suppose we could write it out as this fx, fy, fz, vx, vy, vz. I guess we'll save it for another day, but we'll define these as relative velocities. But this is basically the expression. So this is the only expression that we'll use. So what's important for us to figure out then is that there's some sign convention that's attached to this. We kind of know the sign convention for forces. Forces are always positive in the direction of the positive coordinate system. So if you're summing forces, we take them in the positive x direction, they'd be positive. If they're in the opposite direction, they'd be negative. But there's also a sign convention that matters for this. We've said something about the sign convention, which I've kind of erased, but let me put it back here. This is a sign convention for mass rates, and we have a mass rate that's here. So that will still hold. So if we talk about the mass flow rate, which is going to be equal to density times the area times the velocity, then in terms of our sign convention, it should identically follow this. It's positive outwards. So the sign convention for this should be positive for V2, and it would be negative for V1, because V1 is flowing in there. But we have another sign convention to worry about, and that's going to be the velocity. And the velocity is defined relative to the Cartesian coordinate system, just like the forces. And so this velocity, v2, in terms of just velocity, is going to be positive because it's in this direction, and it's going to be positive because this one also is in the same coordinate system. Right? And so in doing this, almost certainly you'll only use this expression. You probably won't really have to go back to Reynolds transport theorem. You'll use this. But in using this, you just need to make sure that you use the sign convention in the right way. Mass flow rates are always positive going out of the body and negative coming in. And velocities in this expression and forces are always positive in the global direction of the xyz. And as long as you keep that in mind, you should be okay. All right? All right. I think today and tomorrow we'll spend the rest of the time just doing some examples to try and solidify these concepts. So this is just a repeat of exactly what we've said. Maybe it's useful just to do an example to be able to see exactly what this solution should look like. And actually, let's go back to the video, because we didn't look at this video, I don't think. Let's look at this, just because we can. Same principles. Overpressure, a Coke Pepsi bottle, I guess it's Penn State, right? So it has to be Pepsi, not Coke. And it'll fly by the stuff that gets kicked out of the back of it. But the other one is, I guess, I just don't want these playing in the background. Yeah, okay. So this is the example we're kind of looking at. I don't know if there's a narrative on this. Not really. So this is an undershot weir, meaning that the weir blocks the flow, and all the flow that goes through that weir goes under it rather than over it. You see that it's kind of eroded a little pit underneath it, and you can see some of the particles of sand being moved by the motion of the water. Obviously, this is again transfer of momentum. Momentum being transferred from the water to the individual particles of sand, one of which just flipped up there, etc. But we're most interested in the bulk flow of the water, and what we could be interested in would be in figuring out exactly what the forces would be that are applied on this dam. Certainly you could drop this weir or dam down to the base of the bed, in which case there would be an upstream fluid height and a downstream fluid height. If they were the same, the net force across it would be zero. If it was higher upstream than downstream, then there would be a net downstream force. And I suppose you could ask yourself the question, how does that force change if you bring the weir up? Intuitively, if you bring it up all the way till the bottom of the weir just touches the surface, then all of a sudden there's no force on the weir. So I suppose you could intuitively think that if you pull the weir up, then you reduce the force that's applied on the weir. But the question is, can we show that? And so the example that's comes from the book exactly demonstrates that, and just goes through this analysis as an example to make the cases of what we've done. So this is the idea. I could try and show it. So we're going to look at the weir in two different geometries. One is with the gate down all the way to the base, in which case we have a control volume which has the material upstream, and one in which we pull it up and allow flow underneath the weir. And so what we can do in each of those cases is, if we take the first one, we can draw a free body diagram. And the free body diagram could include this component here. Don't know if you can see the red very well. Maybe make a pen with it. So if you look at the forces that are applied on this, the upstream force is this, which are these forces that are applied on the upstream portion. And acting in this direction here is some reaction that's in the x direction. And so there are really only two forces that are applied in that system. We know that the magnitude of this resultant force, Fr, you know how to calculate that, right? It's just the area on this triangle. So Fr is equal to the depth of the centroid multiplied by the unit weight multiplied by the area. and I guess there are some geometric constraints on this. The height of this is h in this case. And so this, if we look at what those individual components would be, the depth of the centroid is just h over 2. The area is going to be equal to uppercase h times whatever the width into the page is, which I think is b. So this is b. Oh, that's the wrong one, right, of course. Bless you. This is just unit weight of the fluid, and this is going to be the height multiplied by the width. So this ends up being something like half gamma h squared b, I think. This term here. And if you just do the free body diagram, it's going to be, and we do it in the positive direction, right? This is positive x. So by definition, FR plus minus Rx equals 0. We know that FR is equal to this, we know it's positive, and we know that Rx has to be the force acting in this, and it has to be exactly equal and opposite to FR, and so we can calculate exactly what Rx is. And so that's the easier one to do. So when the gate's closed, and we go through it, we end up with an expression that is just this, which allows us, since this is equal to 0, to be able to calculate exactly what the reaction is, just by drawing a free body diagram. So now, if we go back in and we raise this gate up slightly, then what we can do is we could draw a slightly different free body diagram, which includes, I guess, this upstream portion, the bottom along here, this part here, this, up to here, and across the top. And now we have similar components to define the behavior. This gate has to be held in by some force, which again is this reaction in the x direction that we'd like to know. The force that's acting on this side of the prism is going to be exactly the same as before, and it's going to be equal to F sub r, and it's going to be exactly the same as this. We have a force that's going to act on this portion here, if you can see the triangle I'm drawing, and this is going to be, I guess this can be FR1 and this can be FR2. And FR2 is going to be a direct analog to this. It's going to be equal to a half unit weight, but the height is going to be this lowercase h squared times the width into the page, the same width here. And so we have this. And so if we calculate those two, that's part of the story, but it's not the full story, right? Because the full story is that we also have mass fluxes that are going across these boundaries. And so if you look at the fact that we have some flow rate that's occurring into this, which is called U1, and we have some flow rate out of here, which we'll call U2, then we have to figure out what the momentum fluxes are that are due to each of those components. And so maybe it's worthwhile me writing here exactly what the expression is that we want to solve. So we want to solve sum of forces in the x direction plus velocity times mass flow rate equals 0. So that's the basic expression that we want to deal with. It's only one component because we're only resolving in the horizontal direction, the x direction. And so what we need to, since we have now both these components, we need to figure out exactly what these momentum flux terms are. This is the flux of momentum out of the system. Some comes in through the upstream portion, and some leaves through the downstream portion. And it's that balance between fluxes that allows us to solve for the problem. So what would those magnitudes be? So if you look at, I'm running out of space, look at the upstream. I'm going to do it slightly smaller. So the upstream is going to be what? It's going to be equal to V1, U1 here, right? Multiplied by the mass flow rate, which is going to be equal to V1 times the density times the velocity times the area, which is uppercase H times B. Right? So this is an area, this is the velocity, so together these three terms represent mass flow rate. And so this whole term represents that. So if we define that, then we need to make sure that we define our terms in the proper way. So the terms that are going to control whether this is positive or negative are controlled by the sign of these things. So at the upstream boundary, U1 is in the direction of the x-coordinate system. So this would be equal to plus V1, if I just write this. The mass flow rate is into the system, and so this gets recorded as a negative mass flow rate. So it's multiplied by minus times density V1 HB. And so this is the right terminology. So if we go down here and we look at this term which is representing this whole behavior, then this is summing all of the individual components. I want to get this. So, okay. So these are the components that represent the forces. So this is the upstream force, which is acting on here. This is FR1. This is the downstream force, which is acting in the opposite direction. It's a negative sign as opposed to a positive sign. This is the reaction, which is negative because it's acting in the upstream direction. And if there's a friction force on the bottom, then that's also acting upstream, and so that's negative. So this is the force balance in equation 3, which defines this system without the green parts added to it. And so the momentum fluxes have to be added to that, which is these terms here. And if we do that, then we can define the upstream flux is going to be equal to this. What's the downstream flux going to be equal to? We can do the same analysis, right? So it's going to be V2 times m dot, which is going to be equal to V2 is in the positive direction, so plus V2, and multiplied by, it's out of the control volume, so V2 is also positive, and multiplied by density times area. Okay. And so now the correct signs for these that we have, good luck, are that the components that we have are equal to positive V2, V2. So the terms that we're looking for are in this momentum term that's on the left-hand side, and this is that term here. And we'd have added to that, if you like, rho U1 squared HB negative. Right? So that all they've done here is they've made an assumption. So here we've calculated each of these momentum fluxes. The one going into the upstream part is negative because the mass flow is into the system, and so this comes out to be overall negative. And the one going out the bottom is overall positive because both of these ones are positive. And if we add those terms to sum up to the components of the forces, we end up with this expression here. So these are the momentum flux terms. These are the two terms. This is the downstream. This is the upstream, which is negative. And the only term that we want to calculate is going to be this. We'll assume that this is 0. We know from what we looked at before the magnitude of the reaction, which we can rearrange. And I guess all I've done here is I've put this extra term in here. The assumption that they've made here is that since this height of the upstream portion is pretty big, then we know that, for instance, U1 times A1 is equal to U2 times A2. And so U1 has to be equal to the downstream, it's small. It's the downstream velocity multiplied by A2, which is a little number divided by a big number. So the fact that this is a large area means that the velocity across here has to be diminishingly small as it gets infinitely large, and so you can ignore the magnitude of U1. That's the assumption they've made. But the bottom line in this is that now that we're calculating the value of this reaction, the reaction before, when we looked at it, was just equal to the hydrostatic force on the back of the gate, which went the full height. So the reaction before was equal to this number. Now, if we pull up the gate, we get two benefits. We have a hydrostatic force which is acting against this magnitude due to the part of flow under the gate, which no longer is pushing on the gate because it's underneath it. We don't care about this, but also the fact this is probably close to 0, but we also get some relief because the signs on both of these terms are both negative. So both of them have the effect that they, not surprisingly, reduce the amount of force that's on the gate. And you could do that just intuitively by thinking about the gate being held in place, hydrostatic force. You pull it up into the limit so it's just licking the bottom of the flowing water, and then there's no force on it. There's no hydrostatic force, and there's no force from the momentum that goes through the system because there's no momentum change going through that block of water. And so it's a useful example to go through. So as we shut down, I'll just reiterate this idea of making sure that you understand the sign convention, and it's just something you have to keep in your mind, and that is that in the same way that we define the sign convention for mass flow rates, that still holds, that mass flow rates out are positive, mass flow rates in are negative, and it's because of this dot product, but the velocities are relative to the Cartesian direction. So if the velocity is in the x direction, then it's positive, and if it's in the negative x direction, well, both of these are positive. Both of these are in the positive x direction. Okay? So what we'll do next time is we'll go through some examples that just maybe cement these ideas into your head just by going through examples.